Yes, we need to do two things today. So first we need to finish the discussion about the linear chain. And then what I would like to do is to extend that discussion to a chain with two atoms, always in one dimensions, because the number of features that emerge when you change the number, when you add up one more particle are quite interesting. So let me finish the discussion about the one-dimensional chain. So here's the model. The model is that of identical particle separated by distance a, each one having a mass m. Right? We label them with I the usual way, I plus 1, I minus 1. And we wrote a solution ui of t, where u is the displacement, right? It's just the displacement of atom I from the equilibrium position. We wrote the displacement in terms of a u double bar e to the I qi e to the I omega t, right? So this was u bar of I, and this was the time dependence. Of course, once again, when I write this, I mean the real part of this quantity. Okay. So this is a time-dependent solution with a given frequency, characterized by a displacement which depends on the position of the atom along the chain. Right? So each atom will have a different displacement because e to the iq, capital I, will be different, of course, because I is different. And all the atoms are moving according to the same frequency. And we verified that this is a solution to the problem as long as the frequency omega is equal to 2 of k, capital K, not to be confused with the other k, over m, absolute value of sine of q over 2. And then we introduce a change of variables. We said that we introduce k, q over a as k. And so therefore, this one becomes, let me write it, k I a, and this one becomes k a. We just change the variable. Oops. So when we plot our solution in terms of omega as a function of k now, k goes from pi over a to minus pi over a, the usual argument. We can go outside, but there's no need to go outside, because if we go outside, we find exactly the same solutions, not only in terms of frequency, but also in terms of the pattern, the way the atoms oscillate. So there's no need to go outside. We restrict our analysis to the Brillouin zone, minus pi over a, pi over a. And if you plot this function in this Brillouin zone, we find that the function behaves something like that. All right? Where this value here is 2 times square root of k over m, right? I'm talking about this value here, which is the value, the frequency, the maximum frequency. And the value of the maximum frequency is taken when k is at the edge of the Brillouin zone. Now, I promised we would analyze these results. We will discuss these results qualitatively. So let me make a number of statements about these results. Now, the first one is about the result at q equals to 0. So when k is equal to 0, the frequency is exactly 0. And I just wanted to notice that this, we should have expected this, because k equals to 0, if you look at the form of the solution for k equals to 0, for k equals to 0, the dependence on capital I disappears, right? So this is a 1. So the solution is the same. The solution is essentially ui of t is a constant times e to the I omega t. Right? So all the atoms move with the same displacement. This one, this one, this one, they move with the same, they all displaced by the same amount. And clearly, if we displace all the atoms together, okay, this is a rigid displacement of the whole system, and there's clearly no restoring force for that displacement. Right? There's no spring that keeps the system back to some equilibrium, because you're displacing everything rigidly. Right? The springs are not even touched by this motion. Okay? Everything is moving rigidly. If you wish, this corresponds to free motion. It's the motion of the center of mass, so that's completely free. It's not constrained. So in our model of harmonic oscillator, this must correspond to a frequency which is 0, because there's no restoring force for that. Okay? So this must be 0. Otherwise, there would be an oscillatory motion, which is, of course, not possible because there is no restoring force. So what I'm trying to say is, of course, yes, let me remark that this solution is not correct for the center of mass in principle. What I'm saying is that it is impossible for the solution to be written in this form, and therefore, if you try to express it in this form, omega must be 0. But I'm not saying that this is the correct solution, because correct solution is a free motion. Right? It's unconstrained. The center of mass moves with constant velocity. Now, the reason why we don't find that solution is that constant velocity corresponds to, in principle, an arbitrary displacement. An arbitrary displacement is not something we... one of our approximations at the beginning of our theory was to assume that displacements were small. Okay? So we were only looking for harmonic solutions around the minimum. So here we find, so I just wanted to try and orient yourself. We don't, if we assume that that was an harmonic motion, small displacements, then the frequency must be 0. But of course, the real solution is something else. Is a constant displacement with constant velocity, which of course could not be obtained through our theory, because our theory was limited to small displacements around the equilibrium position. So in any case, if we try to impose a solution in which the displacement is small, we must get 0 frequency. So this is exactly what we find by constructing the theory properly, with the approximation that the displacements have to be small. Okay, so that's something not unexpected. The translation of the center of mass in the phonon dispersions must correspond to a mode of frequency 0, because there's no restoring force that keeps the center of mass back to some particular position. And there's no spring constant associated to that. Okay. What if k is different from 0, but is small? But small. Small, what do I mean by small? Well, small compared to pi over a, for example. Small on this scale. So k much, much smaller than 2 pi over a. Now, if you look at the solution, we've done it also for a tight binding model. This is e to the I k. IA is the position of atom I in our monatomic lattice. We did exactly the same for a tight binding model. You can recognize that this is essentially position of atom I, because it's I times the lattice spacing. So this one is essentially a wave. In space, if you fix time, if you take a picture, right, you freeze time, what you see is a wave in terms of positions with a wavelength which is given by 2 pi over k, right? So I can also say that this solution corresponds to a wavelength, to a solution with a wavelength given by 2 pi over lambda, or lambda 2 pi over k. Right? This is what this phase means. So in other words, if I have my, let me be a little bit more precise here. This is actually true in general, not just for small k. It is true in general that the solution, if I take a picture, freeze time, this is a constant, this is a constant, the solution in terms of where I am in the lattice, the displacement will be a plane wave with wavelength lambda, if k is equal to 2 pi over lambda. All right? So, if this is I, for example, right, and the displacement is like this, here the displacement could be like this, here it could be like this, here it could be like this. And if I go to negative values, and so on and so forth, right? So it's a wave. Maximum, 0, minimum in the opposite direction, and so on and so forth. In this particular case, I think the wavelength has, if this is the maximum, let me put it here. Here it goes to 0, and then it becomes maximum again. Here it goes to 0. So if I were to plot u as a function of, say, x, right? Well, not exactly like that, but more or less like this, right? And so therefore, this could be the wavelength, for example, lambda. That's not exactly the case because 0 was here, so this is already inverted. Here it's maximum, here it's decreasing, something like that, right? Positive, that's still positive, so here I have to go negative here, and this is a bit bigger, like that. Okay, so I can plot u in this way, but of course u is directed along the x-axis, okay? I'm just using this to show what is the value of u as a function of x, and to show you that this is a plane wave, but the real displacement is this one, it's the one along x, of course. So I'm plotting this function here, e to the I k ri, or e to the I k I a. So what I'm trying to argue now is that if k is much smaller than 2 pi over a, and k is 2 pi over lambda, what this means is that if k is much smaller than 2 pi over a, lambda must be much bigger than a, right? If this is much smaller than this, the inverse of lambda is much smaller than the inverse of a, lambda must be much bigger than a. I think you're all familiar with this, right? We're talking about waves here, standard waves. So what I mean when I take k's which are very small, in terms of 2 pi over a, I mean waves with wavelength much longer than a, to the limit of macroscopically longer than a. So if a is of the order of a few angstroms, typical distances between solids, I'm talking about anything which is much longer than angstroms. It could be microns, it could be millimeters, it could be meters, it could be kilometers, it could be anything. Okay, all this satisfy this condition, so we are talking about something very close to this point here. Now, oscillations with a wavelength which is much longer than the distance between atoms is what carries sound. We all know that if we knock on a system, there's going to be a wave, the atoms are going to be perturbed locally, and this wave of perturbation is going to propagate around our material, and it's going to propagate precisely in this form. But if I knock here, I'm knocking at a frequency which is of the order of hertz, or at most kilohertz. Okay? Actually, if I can listen to the noise, it means that it's between let's say, 100 hertz and 20 kilohertz, right? This is what our ear can listen to, okay? So whatever sound I make is going to propagate through a material with a frequency which is of the order of, 100 hertz to 1,000 hertz. And so because this wave must be given by this solution, after all, these are the solutions of the vibrations in our solid. Sorry, before I said this, I should have mentioned the value of the maximum. Sorry, let me rewind a little bit. Let me discuss first k equals to pi over a. So the limit that, suppose that I'm at the edge, because I need to give you an estimate of this maximum here. So I'm at k equals to pi over a, so I'm here. Yes, I should have done it before. I'm sorry about that. Let me use this side of the blackboard then. So I'm now at k equals to pi over a, and I'll go back to this one in a moment. Let me first discuss k equals to pi over a. First, let me look at the solution. At pi over a, the solution is e to the I I, right? I, right? Small I, big I. Oh, pi, sorry, pi, correct, sorry. All right, so this number is what? If I is odd, it is -1, right? If I is even, it is +1. So if I look at my solutions, if this is plus, this one must be minus. This is plus, minus, plus, minus, and so on and so forth. Okay, so this is a very peculiar mode of oscillation if I'm at its own edge, if I'm at pi over a. It is very peculiar because the atoms move in perfect anti-phase, one close to the other one. If this is moving in one direction, the neighbors are moving in the opposite direction. Now, there's something special about this mode. This mode is the one that allows me to stretch as much as possible my springs. Think of an arbitrary oscillation like this one. If I look at each individual spring, here, for example, they're going the same direction. It is true that this one is longer than this one, but the amount of stretching is the difference between the two, and they both go in the same direction. So I don't have too much of a stretching of the spring. If I want to maximize the amount of stretching of the springs, I clearly have to choose something like that. Here I'm stretching, I'm shortening the length of the spring, and here I'm extending the length of the spring. So I'm doing the best I can do in terms of stretching the springs with a single mode. In fact, that's not surprising that at the end it's going to give me the maximum frequency, because with the same amount of displacement, I can stretch much more my springs. So this mode has to be the stiffest of all the possible modes of my problem. In fact, it is the one with the maximum frequency here. Let me comment also on the value of this frequency. I guess you might be already familiar with the problem of the diatomic molecule. Suppose we have a diatomic molecule, okay? So suppose I'm forgetting about all the other atoms and I keep only two atoms, a pair, with the spring constant K. So I retain the spring, but I'm just removing the interaction with all the other atoms. This is just a diatomic molecule. Mass M. What is the characteristic frequency of this diatomic molecule? Square root of K? Sure? 2m? Sure? So what is the reduced mass?
Okay, you can do it like 1 over k is equal
1 over k.
Is the total k 1 over k.
You're talking about k spring or k,
Yeah,
k spring? There's only one k, right?
Yes.
So
Okay, if we consider that, okay, this is the sum, not the sum, but we have
two masses.
masses. Yes.
All right. So you have to construct what?
The
The reduced mass, not the reduced k, the reduced mass. All right? So reduced mass is, let me call it mu, is what? 1 over m plus 1 over m. 2 over m. So reduced mass is half the mass. Okay? So for a diatomic system, the reduced mass is 1/2 of the mass of the system. So here, I need to put a reduced mass. So there is a 2 here. Okay? So if I had only this diatomic molecule, the frequency would have been square root 2 times the square root of k over m for a diatomic molecule. Here, however, every atom is also connected to the nearest neighbor. So there is an additional restoring force when an atom moves away from equilibrium. If I move away from equilibrium the atom here, there will be one restoring force bringing back the atom to the original position. If I'm in a system like this, if I move an atom out of equilibrium, there will be restoring force due to this one, but also restoring force due to the other one. The mathematics is a bit like the same as the tight binding model. You remember we discussed the electronic structure of a diatomic molecule, and there was this splitting. And then we did it for a tight binding model, and because of the interaction with the nearest neighbors, actually there were 2 interactions, the bandwidth was twice the splitting due to the, in the case of the single molecule. Of course, the physics is completely different, but the mathematics is essentially the same. So here we have that because of the interaction with the nearest neighbors, the maximum frequency, when you manage to stretch the bonds, in this way, is actually square root 2 times this one, because we are now 2 times square root of k over m. So we are square root 2 times larger than the characteristic frequency of a diatomic molecule. All right? So in other words, the diatomic molecule will be somewhere here. Okay? So there will be modes, for some case, there will be modes whose frequency is below that of a diatomic molecule. Think of this one, for example. Here, you're stretching very little the distances between the atoms. In fact, here we have a lambda, which is 1, 2, 3, 4, 5, 6 lattice spacings, which means we are somewhere here, right? We are 1/6 out of the... actually, no, we're more than that. We are 1/12 out of the... so we're somewhere here. So the frequency here will be very, very small. But this frequency, there will be frequencies above this k, in particular when I go to the zone edge, in which the frequency will be larger than that of a diatomic molecule. It will be square root 2 times at most. Now, characteristic frequencies for diatomic molecules are all in the range of terahertz. That's the typical 10 terahertz, 30 terahertz, 1 terahertz, depending on the mass. Or we're talking about periods of the order of a picosecond for the oscillation of atoms in a diatomic molecule. And of course, as a consequence, orders of magnitude, even this frequency will be of the order of terahertz. Okay? So here we are in the terahertz range. That's the typical frequency of oscillation of atoms in solids, in molecules, periods of the orders of picoseconds, 10 to the minus 12 seconds. so 12 to 10 to the 12th hertz oscillations per second. Okay, so we are in the order of terahertz. I'm ready to go back to the limit of small k now, because I do a knock here at the blackboard. The sound is kilohertz now. Kilohertz, we are 9 orders of magnitude smaller than terahertz. That means our frequency is here. There's no other k except k is very, very close to q equals to 0. It can propagate with a frequency which is the sound frequency. Every other phonon, we will not be able to hear it. There will be no, at least, perceptible sound. Whatever we can listen to will have to be 9 orders of magnitude below here in terms of frequency. And of course, as a consequence, also 9 orders of magnitude down in wavelength, of course, or up in wavelength, because it's the inverse of that. So if we are in the Ångström regime at the edge, we will have to be in the meters regime for sound waves. Yes?
Why you don't like k much more than vibrate? I mean, k is in the range between 1
No. I now want to discuss this limit. And I'm arguing that this limit is the limit which is appropriate for sound waves.
Yeah, yes, that's okay, but I mean, which one is appropriate, vibrate or to vibrate? They are the same, I don't know.
Well, this is, for my purposes, they're the same. Factor of 2 doesn't really change my discussion here.
Okay, because, okay, when you say to vibrate, it's just the range.
Yeah, okay, let me put pi over a if you wish. Okay, if you want to be, it's the same. I mean, it's really the same. We're talking about orders of magnitude here, so a factor of 2 is not going to change the order of magnitude. Yes? Here? Okay, so here I'm arguing that these are the possible vibrations that exist in a solid, in a crystal. I'm also noticing that if I do like this on the blackboard, there will be vibrations propagating inside the blackboard or inside anything else. So I now want to identify among these vibrations which are the ones that are carrying the sound, right? So the way I identify the waves that are responsible for sound, which I will call sound waves, I need to have an idea of what is the characteristic frequency of this plot. The characteristic extension of this frequency range is typically of the order of terahertz, because that's the characteristic frequency of oscillation of atoms. Okay? So the typical width of this object is of the order of terahertz. Orders of magnitude, okay? Can be 1, can be 10, can be 100, depending on the system. We are in the 10 to the 12th range in terms of hertz. If this is a sound wave, the frequency of this wave must be kilohertz at most, right? Otherwise, I wouldn't be able to hear it if it's terahertz. Certainly, our ears, at least, they're unable to hear sounds whose frequency is larger than 20 kilohertz. Even bats probably go up to probably 100 kilohertz, but certainly they can go to terahertz. All right. So suppose it's kilohertz, 10 kilohertz. We're still 8 orders of magnitude above here. That means that the sound wave must have a frequency which is extremely low here on this scale. 8 orders of magnitude smaller than the typical scale of this frequency. And because this is a linear function, almost, it must be also 8 orders of magnitude smaller in terms of k, right? In order for it to be a vibration, an existing vibration, one of the possible vibrations of the system. Because only these modes are allowed in a solid, right? So if this is a linear curve like this, then if I'm 8 orders of magnitude below the top, I must be also 8 orders of magnitude smaller in terms of k than pi over a, right? So the wavelength or the k of a sound wave must be 8 orders of magnitude smaller than pi over a. Talking about orders of magnitude, of course. Which means if I express my waves in terms of a lambda instead of k, lambda must be 8 orders of magnitude larger than a. You don't look convinced. Let me repeat. Okay, so these are the only possible vibrations that can exist in a solid. If you have a vibration in a solid, it must have any possible value of k, but once you fix k, this must be the frequency. Or vice versa. If you tell me the frequency here, I can tell you what is the k. All right? Sound waves, kilohertz, must be very small in frequency. So the only possibility is that they are here. Very small values of k. 8 orders of magnitude smaller than the maximum, 9 orders of magnitude. Similarly, also, k must be 8 orders of magnitude smaller than the edge. No? Okay? So as a consequence, lambda for sound waves, so here let me discuss sound waves. Okay? By definition, a sound waves is something where omega is of the order of kilohertz. Let me forget about 2 pi. I mean, it's orders of magnitude, okay? And therefore, lambda must be of the order, is 8 orders of magnitude smaller than angstrom. So we are in the meters range, right? Actually, well, centimeters. These are sound waves. But the physics of waves also tells us that there is a velocity associated to, let me call it c. It's not the speed of light, but it's the velocity of waves, right? Which is given by omega over k. Yes?
So we saw omega, the frequency can be 0, right?
The frequency can be 0, yes.
Yeah, all right.
But then k has to be 0.
Yeah. And then we consider as if they are connected by a string, and then now we can find an analog like with harmonic oscillator, right?
Yes.
We say the ground state energy like have h bar omega, and then I don't know.
There's no quantum mechanics here. If you wish, we can talk about the quantum mechanics of the consequences of the problem. But so far, I haven't been discussing about anything that has to do with quantum mechanics. It's purely classical mechanics here. I can perhaps digress, but let me do it at the end, because otherwise it's a bit confusing. No quantum mechanics here. It's just classical mechanics.
Okay, because if the frequency can be 0, then the ground state energy
Yes?
can also be, there is a probability of being 0, right?
Yes, if you wish, yes. But take into account that if we go to q equals to 0, you're displacing the whole system rigidly. So it's something with infinite mass that is moving, in principle, because it's an infinite system. So the mode at k equals to 0 is a mathematical concept, but in practice there's little analogy with the real system. You'll never be able to probe exactly k equals to 0, because you would have to be displacing rigidly the whole system, an infinite system. Okay. While the limit of small k's, large wavelengths, is something physical, because it's what you have in sound waves. So I guess you're all familiar with this relationship, right? Where c is whatever the velocity of the waves has to be. If you have a wave propagating with a given frequency and a given momentum, or a given 2 pi over lambda, right? You can say that, well, if you wish, you can also write it as nu times lambda, right? Which is the same. Frequency times wavelength. And standard waves have this velocity being a constant. Of course, here, the velocity, which is omega over k, is a constant only as long as this is a line, right? Omega proportional to k. So there is a range of k's for which you can safely say that this is a constant. Then, of course, the slope changes, and you can no longer say that omega over k has a constant speed. So it is a wave-like motion, but where the velocity depends on k. So this is a bit more complex than usual. Yet, for small k's, which are the ones that are of interest to us, because sound waves are at small k, we can safely say that there is a velocity, and that this is given by omega over k. It's the same throughout this initial part of the phonon spectrum. Okay? So this slope here is the sound velocity. Something which we can measure, right? I don't know if you have an idea, say, you know what is sound velocity of a standard system of, say, the blackboard or is this piece of aluminum? How fast do sound waves propagate in this kind of, in almost any order of magnitude, do you know? Do you know the speed of sound in air? 300 meters per second, right? What about in solids? Slower, faster? Faster, much faster. Typically at least one order of magnitude faster than in air. So say for metals, it's typical of the order of 3, 4, 5,000 meters per second. So we're talking about kilometers per second in ordinary solids. So this slope here is typically of the order of kilometers per second. By the way, you probably could have guessed this. If I tell you this is terahertz, and this is, say, the inverse of a nanometer, 12 orders of magnitude, 9 orders of magnitude, so it has to be 10 to the third meters per second, orders of magnitude. Okay? So as soon as I tell you that this is terahertz, if you know that this is the typical distance between atoms, you can also guess what could be the sound velocity of at least orders of magnitude. What is the typical sound velocity in a solid? We're talking about 10 to the third meters per second. And of course, the way the atoms vibrate is still like this when I do this. So when I do this, the atoms in the blackboard will oscillate with this periodicity, of course, with a lambda, which is several centimeters up to a meter. That will be the wavelength. And the frequency will be kilohertz, depending on what is the actual sound of the knock. Okay, so atoms here in the blackboard are indeed oscillating like this with the wavelength of macroscopic size, centimeters, and the frequency in the kilohertz range, 100 hertz to kilohertz range. So the important, I think, take-home message here is that we have been able to connect a microscopic property like capital K, which is the spring constant between two atoms, like the mass of the atoms, to something which is really macroscopic. Sound is really a macroscopic event, a macroscopic phenomenon. But here we have a clear example of how a microscopic theory, an atomistic theory, allows us to say something about a macroscopic phenomenon like propagation of sound waves. By the way, if I can digress, sound velocity is also what we measure when there is an earthquake, and you measure the velocity of the seismic waves. Seismic waves are sound waves, essentially. Okay, so when you measure the time it takes for an earthquake to arrive from the point it has been generated to a detector located perhaps on the other side of the Earth, okay, it may take hours. Well, hours probably not, but certainly several minutes to get from one side to the other one. Well, it's, say, kilometers, 5 kilometers per second, so the Earth, the diameter is what, 10,000 of the order of 10,000 kilometers, so it takes 10,000 seconds. So it can take 2 hours, 3 hours to get from one side to the other one of the Earth. And the seismic waves generated on one side to the other one. So by measuring that, the speed, the time it takes for an earthquake to get to the other side of the Earth, and determining the velocity, therefore, of the seismic waves, we can extract very, very interesting information about the sound velocity, of course, of the materials that compose the Earth. So in principle, if we had a theory that allows us to predict the sound velocities of minerals, of the objects that compose the Earth, we would be in a position to predict also what would be the velocity of seismic waves. So this is actually a very interesting field of study. I'm just mentioning because it's a very interesting and recent field of study that connects earth sciences with physics, because in physics you can either predict, you can measure, or you can calculate sound velocities. And these sound velocities, if you're able to predict them for the minerals that compose the Earth, that will give important information about the velocity, the propagation of seismic waves, and therefore you can make predictions about what is the Earth composed of, what kind of minerals compose the Earth. Of course, we know nothing about what's inside, right? We just know it because we know roughly the density. We only know about the density and the velocity of seismic waves, about the materials that compose the Earth. There's nothing else we know. So the fact that there is a nucleus, a core made of iron, we only speculated because of the density and because of the velocity of seismic waves. It could very well be something else. It could be nickel, for example, or some other material. So it is very important to come out with methods, independent methods, to calculate, predict, and detect the sound speeds in solids if you want to know more about the Earth, the internal regions of the Earth. Okay. I think I need to stop here with the monatomic chain. I need to move on to the diatomic chain. Is there any question about this? Okay. So let me move on with the second example. We're just going to make our life slightly more difficult than we've done so far. We're going to introduce a system in which we have, instead of having one single atom, so we're now going to do the diatomic chain. So 2 atoms instead of 1. So the model is now the following. We have a part, okay, so we have X here, and then we have a system made of 2 atoms per unit cell, okay? And of course we have now 2 springs, a very stiff one, which we call G, and a very loose one, which we continue to call K. Stiff one, loose one. Okay, so we have 2 spring constants in our system, and 2 atoms, of course. For simplicity, let me assume that the 2 atoms have the same mass. I can take atoms with different mass, but our calculation will be slightly more complicated for no reason. Now, the unit cell of this system. Well, the unit cell of this system is actually, it's say from here to here, right? That's the unit cell, A. The unit cell has 2 atoms inside with same mass. They can be identical atoms. The only reason why they are different is because they are connected to the left and to the right to the stiff spring, right? So they differ. So we have 2 atoms in the unit cell. And let me give it a name. So this would be atom 1, for example, and this would be atom 2. I just give it a label. So this is cell I. This will be cell I plus 1, and this will be cell I minus 1, right? So I label with I the cell, and within a cell, I label the atoms, the bases, with 1 and 2. Okay, so this is the Bravais lattice, and this is the 2 atoms in the bases, using our language of crystal structures. So simply have to sit down and write down the equation of motion. So for this, So let me do now we'll have two equations of motion because I will have two atoms in the cell. So let me do atom 1 now. So for atom 1, I will have mu1, well, let me, second derivative with respect to time, that's the force, well, that's acceleration. This will have to be equal to minus g. So I'm now looking at the interaction between 1 and 2. Right? So this will be proportional to u1 minus u2. Oh, sorry, I. So this is atom 1 in cell I. Will feel the restoring force due to atom 2 in cell I. So I have to calculate the relative displacement between the two atoms. We're still in one dimension, right? So I'm doing exactly what I did before, simply I'm now, instead of putting here u of I plus 1, I have to put an nearest neighbors, which is actually u2 of I, right? It's not another cell. It's the same cell, it's another atom in the same cell. To the left instead, this is going to interact with a spring constant K, which is different. u1I minus this atom here, which is atom 2 of cell I minus 1. And same for atom 2. Atom 2, cell I, will interact with spring constant K with u2I minus u1I plus 1, right? Atom 1 of cell I plus 1. And will interact with atom 1 of the same cell with spring constant G, this spring here. So now I have to make a guess for the solution. For example, for u1I of t, well, let me make exactly the same guess. U double bar e to the I omega t e to the I q I. But it's 1, so I have to put 1 here. And of course, for atom 2, I simply have to change u double bar. So with respect to what we did before, we have to determine now omega for a given q, but we also have to determine u bar 1 and 2. So this is not just a one scaling. There might be a relationship between u bar 1 and u bar 2 that we have to find out. So before there was only one u double bar, and that was just the intensity of the vibration. Any value of u double bar was okay. It's an oscillation, so the frequency will be the same for every, say, displacement. Here, we will have the possibility to play with u bar. You'll see it in a moment. Play with u bar 1 and u bar 2. Okay, so I'm going to now use this ansatz, this guess, to solve this. So I'm going to put it inside there. So the first line will become m minus omega squared, which comes from the second derivative, omega is the same, times u double bar 1 e to the I omega t e to the I q I. All right? Equals to minus g u1 double bar 1 e to the I omega t e to the I q I. u2I u double bar 2 e to the I omega t e to the I q I. And that's done. The second part here, minus capital K u double bar 1 e to the I omega t e to the I q I minus u2 double bar e to the I omega t. And here I have to be careful because this is I minus 1, right? So it's q I minus 1. Second line, it's more or less the same. Equals 2 minus capital K u bar e to the omega t e to the I q I minus u1 e to the I omega t e to the I plus 1. Minus g u2 e to the I omega t e to the I q I minus u1 double bar e to the I omega t e to the I q. All right. Allow me to remove e to the I omega t everywhere. Allow me to remove e to the I q I everywhere. Okay, here I have to remove the I. I remove the I. All right? Good. And allow me to change sign everywhere. There's a minus here, minus, 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 right? So I can change sign everywhere. So, omega square m u1 double bar is equal to minus g u1 double bar minus u2 double bar minus k u1 double bar minus u2 double bar and then e to the minus iq. Yeah, sorry, I just told you. Yes. Thank you. And then okay, actually let me leave it like this. Okay. E to the I q plus g okay. Now, if you remember last time, when we got to this point, we only had one equation. And the equation could only be solved if omega squared was sine of something. Now it's a bit more complicated because we have a system of two linear equations and two variables, u bar 1 and u bar 2, which we need to solve. So our unknowns, let me remind you, are omega, u bar 1, u bar 2, and q. These are all our unknowns. Last time, mean, for the monatomic chain, once we found the relationship between omega and q, U bar could be anything. Of course, non-zero, because otherwise that would have been a trivial solution. Okay, so I'm sure you recognize here a 2 by 2 problem. Right? Let me write it as a 2 by 2 problem. First, the right-hand side, G plus K minus G minus K e to the minus IQ minus G minus K e to the IQ G plus K all right? So now instead of having a single linear equation, we have two linear equations coupled. And the problem from a mathematical point of view becomes equivalent to a diagonalization of a 2 by 2 matrix. We need to diagonalize this 2 by 2 matrix, see whether we get positive eigenvalues, because the eigenvalues must be positive, if they want to, I mean, if we want to find a frequency that satisfies these eigenvalues. And the eigenvectors, U1 and V2, U bar 1 and U bar 2, will be the solutions for that particular Q and omega. So essentially, what we need to do is to diagonalize this 2 by 2 matrix. Notice that it's Hermitian, right? Because if I take the complex conjugate of this one, I get the other one. So it's a good matrix, it's Hermitian, so there will be eigenvalues. Whether they will be negative or positive, I cannot tell, at least not from looking at this. So I need to diagonalize it. Now, we're not going to diagonalize it here. It might, I mean, it's not so difficult, but it's not simple either because of this phase here that will make our calculation very tedious. So I'm just going to diagonalize it for specific values of Q. Not for all possible values of Q, but I'm just going to do it for specific values of Q. And then we will connect the solutions. So pi over A minus pi over A, 0, omega. Let me start with the simplest, K equals to 0, or Q equals to 0, which is the same. So let me set Q equals to 0 here. What happens? We have G plus K, G plus K, minus G minus K, minus G minus K. I have to diagonalize this matrix. A minus A minus A. What are the two eigenvalues?
0 and 0.
Exactly. 0 twice A. All right? Well, twice G plus K. So here I have two solutions, this one and this one, assuming that this is twice. Oh, sorry. In terms of omega, of course, omega squared times m is equal to this one. So this is actually square root of 2g plus k over m. All right. Let me take Q equals to pi over A. pi over a, this becomes -1. So allow me to do it here. Plus, plus. I've changed it into a plus, right? Because e to the I pi, if k is equal to pi over a, q is equal to pi. So e to the I pi is -1, so I'm changing the sign of k there. So it's plus. Now it's no longer a minus a, but it's a b, b. So the two solutions are
J and 2K.
2g, okay. Let me do it slowly, because so it's g plus k plus or minus plus k minus g and g plus k minus k minus g. But I assume that g is larger than k by definition, by construction. So this is g minus k, actually. So this is equal to 2g, and this is equal to 2k, right? Because g is larger than k. All right, so the solutions, the two frequencies are square root of 2g over m, square root of 2k over m. Now, they're both smaller than this one, because this is g plus k. The other ones are g or k. And g is larger than k, right? So I will have here square root of 2g over m, and somewhere here square root of 2k over m. And of course, similar here and here on the other side. Now, well, I would need to, of course, calculate it, but I'm now going to just draw it and assume we have done the calculations properly. There are good reasons to say that here the derivative must be flat, because this function must be periodic, right? Like for the band structures, the electronic band structures, these functions must be periodic. So the derivative here must be flat. Same here. I mean, if I want to connect these 3 points and build a periodic function, the only possibility I have is to do this, right? So that it continues periodically. Of course, this point could also be connected to this one instead of to this one, right? So here, I would actually need to solve the problem in order to prove that this is the solution. It could be that this one is actually connected to this one, and this one is connected to this one. There is a crossing. But, I mean, if you actually do the calculation properly, you realize that there's no crossing, and this is the actual solution for every value of q or k. Sorry. Okay. Sorry, k equals to pi over a, yes. Or q equals to pi. Yep. Yep. So I'd like to discuss differences between this and the previous one, the monatomic chain. The first obvious difference is that here, for every value of k, I have two solutions, right? For the monatomic chain, I only had one, not two. But it's easy to trace back to our, model why we have two solutions. We have two solutions because for every q, we have a 2x2 matrix problem to solve. So we're going to have two eigenvalues. Why do we have a 2x2 problem? Well, because in our equations, we had to introduce two different equations for the two particles. All right? So the number of solutions is actually given by the number of particles in the unit cell. If I have 3 particles in the unit cell, I'll have 3 equations. I'll end up with a 3 by 3 matrix to diagonalize. I'll end up with 3 modes. So there are some, I'm now going to make some statements which are very general and not specific to these models. Although I'm not going to prove them exactly, they are quite obvious. So the number of moles is equal to the number of atoms in unit cell. Let me add one dimension. Suppose I'm in 2 dimensions. I'm not going to do the exercise again. But suppose I had one particle in 2 dimensions, a square lattice, for example. Each particle, one particle in the unit cell, is characterized by 2 Cartesian coordinates. So when I build the equations of motion for that one particle in 2 dimensions, I will have ux and uy. So I will have 2 equations. If I do all my derivation, I will end up with a 2 by 2 matrix, even for one particle, because of x and y. Okay? So here, I have to remember to take the product with the dimension of the system. Right? In 1 dimension, it's the number of particles. In 2 dimensions, it's twice the number of particles, because each particle will have 2 independent directions. In 3 dimensions, there are 3 Cartesian directions, and therefore each particle carries 3 independent degrees of freedom. Right? So the number of moles is the number of atoms in the unit cell times the physical dimension of the problem. If we're in 3 dimensions and we have 1 atom per unit cell, the number of moles will be 3. First important statement. Suppose I'm now at Q equals to 0, at the zone center. Here we have 1 mode which is 0 and 1 mode which is non-zero. We're going to analyze in a moment what is the meaning of this mode. In the previous case, 1 atom per unit cell, we only have 1 mode, and that the frequency was 0. What if we have 3 particles per unit cell? Well, 3 particles per unit cell, we're going to have 1 mode with 0 frequency and 2 modes with finite frequency. The reason why this is so is because this mode, as we already argued, is the translation of the center of mass. Okay? So in 1 dimension, we only have 1 mode that corresponds to the translation of the center of mass. So at Q equals to 0, we have a number of modes with omega equals to 0, which is equal to the number, to the dimension of the problem. Sorry. Number of modes with frequency 0 is equal to the dimensions of the problem. In 1 dimension, it's 1. In 2 dimensions, it's the center of mass in 2 dimensions, 2 degrees of freedom. In 3 dimensions, it's the 3-dimensional displacement of the center of mass. So at Q equals to 0, you'll have a number of modes with 0 frequency, which is equal to the dimension of the problem. Okay? Which means, obviously, if you have a single atom in the unit cell, the total number of modes is the dimension of the problem. At Q equals to 0, you have modes at omega equals to 0, which is equal to the dimension of the problem. So you have no modes at Q equals to 0 with finite frequency. In order to have modes with finite frequency in a crystal, you need to have more than 1 atom per unit cell. If you have 1 atom per unit cell, you have to have a number of modes with 0 frequency, which is equal to the total number of modes at Q equals to 0. So no chance to have finite frequency at Q equals to 0. Okay, so I'm now arguing about the modes that have 0 frequency at Q equals to 0. We notice that these modes are the translations, the rigid translation of the whole system. So in 1 dimension, there is only 1. the possible, there's only one mode. Okay? In 2 dimensions, there are 2 degrees of freedom, so I can translate my problem like this or translate my problem like that. So there are 2 independent directions that I can move my system. So I will have 2 modes with 0 frequency in 2 dimensions. In 3 dimensions, I will have 3 degrees of freedom. So I will have 3 modes with 0 frequency. So regardless of the crystal, of the number of atoms in the unit cell, I will always have a number of modes with 0 frequency equal to the dimension of the problem. 1, 2, or 3. Okay? Now, let me connect it to this statement here. The number of modes at any value of q is equal to the number of atoms in the unit cell times the dimension. Suppose that I have 1 atom per unit cell. Number of atoms per unit is 1, so the number of modes at any q is equal to the dimension of the problem. If I look at this one, at q equals to 0, the number of modes with 0 frequency is equal to the dimension of the problem. All the modes have frequency equals to 0. All right? So if the number of atoms in the unit cell is 1, at q equals to 0, I don't have anything else other than modes at 0 frequency. Okay? Okay. Other general statements. Well, obviously, the number of modes still at q equals to 0. The number of modes with frequency strictly different from 0 is equal to the number of atoms in unit cell minus 1 times the dimension of the problem. Right? Because number of atoms in unit cell times dimension minus the modes at 0 frequency, which is the dimension. Okay? So it's n minus 1 times the dimension of the problem. So here, one-dimensional problem, 2 atoms per unit cell, 2 minus 1 is 1 times 1, 1. So I have 1 mode with frequency different from 0 and 1 mode with frequency equals to 0. Here you go. In 3 dimensions, which is the typical example, real examples, for monatomic crystals, no modes with frequency different from 0 q equals to 0. Okay. What is this mode in this particular case? What does it correspond to? Well, it's I should have I removed the matrix, the 2 by 2 matrix there. Okay, I'll have to discuss it qualitatively, otherwise I have to go back to the matrix. If you remember, the matrix here was A, right? This one is the eigenvalue with 2A, and this is the eigenvalue 0. The eigenvalue 2A, the sum of these things, is actually the one with the anti-bonding sum. So it's the case in which U1 is equal to plus 1, and U2 is equal to minus 1. You can actually prove it with your matrix. I don't want to now rewrite the matrix and recalculate it. You'll find out that, well, if you want to normalize them, you also put a square root of 2 just to normalize them. Anyway, it's the mode with the opposite sign, the one that gives this mode. Well, obviously, you recognize it from the fact that this is the one with minus sign. You argue it from the fact that this one, which was the 0 mode, is the translational mode. So the 2 atoms have to be moving together. So the 2 displacements have to be the same. So obviously, this one is the one with the displacements being the opposite. So if I look at this one, this particular mode is the mode where the particles move like this, one against the other one. This one here. Now, of course, this is very similar, the analog of the mode at pi over a in the monatomic chain. But it's not the same, because this is a Q equals to 0 mode, because all the atoms in the unit cell do the same when you go from one unit cell to the other one. Okay? So that's important, this distinction between the two cases. Here, atoms can move against the other one, even at Q equals to 0, because there are two atoms per cell. And so if the two move one against the other one, as long as they do the same in the other cell, that's fine. That's the Q equals to 0 mode. They do the same in all the cells, although the two atoms inside the cell go in opposite directions. Yet, this mode is the one that is reminiscent of the mode at pi over a in the monatomic chain. Now, in the last 5 minutes, we're going to discuss a paradox. Suppose that G becomes equal to K. It is a possibility, right? Suppose now that G, we make it equal to K. All right, well, there are a number of interesting things. First, these 2 points merge, become the same point, right? There's nothing wrong with that, right? We can do that. We can put G equals to K. These 2 points merge. This point becomes 4 times G, or 2 times square root of G over M. But notice, look at this. If I make G equals to K, I never used in my theory the fact that these two atoms are closer than these two. I never used the distance in my theory, so they could very well be at the same distance in principle. The only thing that distinguishes the atoms is the spring constant. And I'm now going to make G equals to K. Okay? But if I make G equals to K, there's no reason why I should choose a unit cell containing 2 atoms. Right? They're identical. One cannot be distinguished from 2. Distances don't matter, because I've never used the distance here, so I could place it at equal distance. The only thing that really makes one different from G is that one has G on the right and K to the left, and 2 has G to the left and K to the right. But as soon as I make G equals to K, the distinction vanishes. So if G becomes equal to K, we're going back to the previous lecture, right? Monatomic chain with the restoring constant G or K, whatever I want to call it. So from a physical point of view, we are recovering exactly a problem for which we know the solution quite well. We did it last time. We discussed it today. But in this particular case, the only thing that we find is that these 2 points coincide. We have 2 branches, we have modes at Q equals to 0. That's different with respect to what we did before. So the question is, what's happening here?
The conclusion that we did is not valid when J is equal to K.
No. Was there any point in which we assumed that J was different from K?
Maybe the eigenvalues, the eigenvalue problem.
No. You can repeat it, and it's going to be the same. Yes?
We are taking our unit cell twice the unit cell.
Exactly. Here, A doesn't have the same meaning. A before was a single unit cell. So let me call it A prime here, because A prime is actually twice the original A of the monatomic cell. So if I here put A prime, which I should put A prime, because now A prime is my thing here, well, this is actually 2A in terms of A. So? Why is this maximum here now? Okay, fine. The value of the maximum was recovered because it's 4 times G or K. I take the 4 out and it's 2 square root of F. So maximum is fine, but why is it here and not here?
We fold the one in the second reading into
pi over 2a, right? The other maximum was here, pi over a, here. All right? So what we have done is simply describing a system which could be described with a unit cell given by a. We are now trying to describe it with a unit cell which is twice as large. Of course, if the unit cell is twice as large as the one we should use, the Brillouin zone is also 1/2 of the size of the one we should be using. So of course, the modes will have to appear somewhere and will be just translated by pi over a, or 2 pi over 2a in our spectrum, right? So this mode here is the one that originally was there. But we had to translate it here in order to bring it inside the Brillouin zone. Right? We could keep it there, no problem. But it's better to bring it inside the Brillouin zone, at least in our assumption that everything should be brought inside the Brillouin zone. Okay, so that what looked like a paradox is actually not a paradox, because we need to remember that we've changed the size of the Brillouin zone, and therefore of the unit cell, and therefore of the Brillouin zone by a factor of 2. Ooh. 1 minute just to tell you that this particular mode is very interesting. Of course, if k is different from g, because otherwise it doesn't make sense to consider it. Particularly for systems in which the two atoms have two different charges. Think of an ionic crystal, for example, in which this particle could be charged plus and this particle could be charged minus. Okay, in 3 dimensions, of course, it's different. In 1 dimension, this could be plus and minus, like sodium chloride, for example. Because this mode corresponds to the stretching of this, I'm going to change this mode corresponds to a stretch of the dipole moment of my system. So I have a dipole moment when the system is oscillating with frequency and with particular mode. There will be a collective change of the dipole moment of the polarization of my system. And therefore, there will be a coupling of this mode with an external electromagnetic radiation. Right? Because whenever you have an electric field, you can couple it with an external electric field. And in fact, you can even drive this mode by applying an electromagnetic field with this frequency. Because the electromagnetic field will make your particles oscillate and will induce this dipole inside the system. So if you want to see the atoms moving at this frequency, it's enough to send an electromagnetic wave and with this particular frequency, and the atoms will oscillate with that frequency because they will couple to the electromagnetic field because of the fact that they generate a dipole moment when they vibrate. So all this is the fundamental principle that makes infrared absorption, infrared spectroscopy possible. You might have heard about infrared spectroscopy. It's a very powerful technique, particularly in chemistry, in organic chemistry, to detect vibrations in solids, in molecules, in crystals, and is essentially based on the excitation of Q equals to 0 modes at finite frequency due to the coupling with the dipole moment of the internal dipole moment of the problem, of the system. So I just wanted to mention that these particular modes are very interesting, very studied extensively in solids, particularly molecular crystals and in organic crystals. I think that's the end of what I wanted to say. Is there any question? Yes? Yeah. Oh, velocity of sound here is always this one, right? It's the argument is the same. You have to look at low frequencies, and if you look at low frequency, you have to restrict yourself to this area. So you have to look at the velocity of sound will be the one given by this slope here.
What about the ultrasonic vibrations, which are...
You mean here?
Yes.
No. With whatever you call sounds terahertz, think of this as terahertz. So if you're talking about kilohertz, you must be here. There's no other chance. If you want to go here, you have to go to terahertz. So it's really almost optical frequencies. Well, but you have to, this is no longer sound, it's something else. Yeah, it is vibrations with this. Oh, you mean here the velocity is 0, for example? Yes, it is 0. Yes, these waves here propagate with 0 velocity, so they don't propagate, in fact. But you shouldn't really be seeing them as sound, because this is not sound. This is terahertz excitations, microscopic vibrations. Whatever has to do with sound typically has a well-behaved linear slope, so you can clearly see it as sound. Of course, if you're interested in sound, you can forget about the rest. I mean, you just focus on this range here, and you're done. Which one? This one? Well, k equals, well, you have to construct the mode. Q equals to 0 means that there is no wave. The atoms do exactly the same in all the cells. Okay, so here there's nothing propagating here. More questions? Okay, so that's the end of the course. Oh, questions. Okay, I think we can stop probably here, and then we take questions.